Hello, I'm Philip Liang, and I'll be teaching a video lesson on risk attitudes in this video. So risk attitudes are going to help us describe how people make trade-offs between risk and reward. So we'll use the stocks and medium risk corporate bonds example from a previous video. So we're going to assume that stocks have a 27% chance of providing a return of minus 13% and a 73% chance of providing a return of 21%, while medium risk corporate bonds have a 16% chance of a minus 3% return and an 84% chance of a 9% return. So we observe people buying both stocks and bonds. So even though the stocks have a higher expected value, there must be something appealing about the bonds. And the bonds are appealing in that there is less risk of losing money. Both the chance of loss and the magnitude of loss are lower. So when we're modeling risk attitudes, we can model the fact that bonds appeal to some investors who don't have an appetite for high risk investments. So this expected utility function U is going to help us model preferences over wealth. So here we'll explain what properties we need U to have. So if X and Y are some random outcomes, U is going to describe someone's preferences if and only if X is preferred to Y, if and only if the expected value of U of X is greater than the expected value of U of Y, and a person is indifferent between X and Y if the expected value of U of X is equal to the expected value of U of Y. I will note that the expected utility functions of two different people are not comparable. And another thing to note about expected utility functions is that the relative magnitude of differences can say something about preferences. Essentially, if U of X equals 0, U of Y equals 1, and U of Z equals 10, there is some real sense in which Y is more similar to X in terms of payoff than Z, because this would imply that the person would be indifferent between a 90% chance of X and a 10% chance of Z and an 100% chance of Y. All right, so now having described the expected utility function, we can go ahead and define risk attitudes. So we'll think about a certain payoff C and an uncertain payoff U with the same expected value as C. So a person's going to be risk averse if C is preferred to U. So a risk averse person prefers certain to uncertain payoffs, holding expected value constant. A person that's risk neutral is indifferent between C and U. So the attitude towards risk is indifference, holding the expected value constant. And person is risk loving as U is preferred to C. So the person actually prefers the risky bundle to the safe bundle. So now with this framework, we can think about decisions under uncertainty. And thinking about decisions under uncertainty can get a little bit complicated, especially if we've got multiple actors going on, multiple sources of uncertainty. So here, there are going to be two sources of uncertainty in this problem. A home I own that's worth $250,000, but might be destroyed in the next year by a fire with a 1 in 800 chance. And there is commercially available fire insurance costing $400, and this will give me the money needed to rebuild my home if it does burn down. I'm also going to have 100,000 of savings. Now I have two options for those savings. I could either invest them in the stock market, which gives me a 27% chance of losing $13,000 and a 73% chance of making $21,000. And here I'm going to assume that the chance of my house burning down is independent of stock market performance. The other thing I could do with my savings is invest them in a savings account. This will earn me a guaranteed $1,000 of interest. And my utility function is going to be U of W equals -1/W, where W is the dollar value of my wealth. We're ready to start discussing risk attitudes. So suppose C is a certain payoff and a U is an uncertain payoff with the same expected value as C. So a person will be risk averse if C is preferred to U, holding expected value equal. The person prefers to avoid the risk rather than to take the risk. A person is risk neutral if that person's indifferent between C and U. So a risk neutral person does not care whether a bundle has risk or no risk. And a person is risk loving is U is preferred to C. That is, a risk loving person prefers risky things to certain things of the same expected value. All right, now we can put this all together and analyze a fairly complex decision under uncertainty. So we're going to have two sources of uncertainty. The first is going to be the fire risk on my home, which is a home worth $250,000 that has a 1 in 800 chance of being destroyed by fire next year. And I can spend $400 to insure my house against fire for the next year. And the other potential source of risk is I have $100,000 of savings, which could either be invested in the stock market, giving me a 27% chance of losing $1,300 and a 73% chance of making $2,100. And I will assume that the stock market performance is independent of my home burning down, or I could invest my savings in a savings account and earn a guaranteed $1,000. And my utility function is going to be U of W equals -1/W, where W is the dollar value of my wealth. Now we can use risk aversion here and analyze my utility function. So we can see that my utility function flattens out as my wealth increases. And we can also consider specific risks, such as a risk of fire. Let's say right here is a 50% risk of fire, and the expected value of that damage is 125,000, but it gives me utility all the way down here, right between being homeless and having all my wealth intact. And right here, I can see that this is actually about as costly to me as losing $200,000 of wealth. So I dislike the risk of my house burning down even more than the loss of the expected value of that risk. All right, now we can start working on solving. So the first case I'll consider is no insurance in the stock market. So using independence, we'll get the probability of these two events happening together. So the best thing for me is if my house doesn't burn down and I make money in the stock market. So this probability is obtained by multiplying the probability of each of the independent events together. And in this case, I'll have a house plus some investment account that's increased in value, and that'll work out to 371,000, and that's with probability 0.7290875. So the probability my house doesn't burn down, but I lose money in the stock market is 0.2696625, and my net worth here is going to be my house plus what's left of my investment, which is going to be $337,000. Now, if my house burns down and I make money in the stock market, my net worth is going to be 121,000, and that's going to happen with probability 0.009125, and the probability my house burns down and I lose money in the stock market is 1/800 times 0.27 equals 0.003375, and all I'm going to have left in that case is $87,000. Now, taking the expected value of my utility function is going to get me minus 2.7768 times 10 to the minus 6. Let's next consider the case where I buy insurance and also invest in the stock market. So the probability that I make money in the stock market is 0.73. And if I make money in the stock market, I have my house plus my brokerage account minus my insurance premium, which comes out to $370,600. And the probability I lose money in the stock market is 0.27. And again, if I lose money in the stock market, my net worth is going to be my $250,000 house minus $400 of insurance premium plus $87,000 in my stocks. So my expected utility will be minus 2.77192 times 10 to the minus 6. And if I have no insurance and deposit my money in the savings account, then the probability that my house does not burn down is 799/800. And if my house does not burn down, I have my house plus my savings account, which is going to be worth $351,000 in total. And there's a 1 in 800 chance my house burns down, and then I only have my savings account, which gives me an expected utility of negative 2.85782 times 10 to the minus 6. And then if I have insurance and a savings account, my net worth is certainly my savings account plus my house minus my insurance payment, which comes out to $350,600, and my expected utility is minus 2.85225 times 10 to the negative 6. So here I have my payoffs summarized in the table from the various options. You can see that the stock market and insurance is the best option with the highest utility. And also note that holding the insurance choice fixed, the stock market always improves utility. And this occurs because it offers significantly more upside with a moderate amount of risk. The expected value of insurance can also be calculated. I lose the $400 premium, and there's a 1 in 800 chance I could make a $250,000 claim, which comes out to an expected value of minus $87.5. And the insurance, although it has a negative expected value, will improve utility, as we can see from comparing the two options with the savings account and the two options with the stock market, because it protects against the significant loss at a low price. So this example also shows that it can be rational for risk-averse people to make risky and safe choices at the same time. Risk might be insured even at the cost of expected value when the risk is serious and the protection's relatively cheap, while risk might be borne when the incentive to bear risk in terms of expected return is high enough.